Hello everybody and welcome to another video. So here I'm introducing the series of C exceptions implementation, where we will be trying to implement exceptions from the ground up in C. And I'll walk you through the implementation sort of on theoretical basis more so than us breaking down the assembly output. It's just I'm going to talk about it in theory, but I'm going to talk about the implementation of C++ exceptions and how they can be better in certain situations and they can be worse in other situations. So first off, let's think about what's the first approach that comes to mind, and quite frankly, what's the most common approach to try to re-implement the exceptions in C. By the way, just to give you some background, I am using Quicksort algorithm and code logic to showcase how we're gonna throw exceptions, and Quicksort is really a good function, or even a function that could be relatively good as well is, and relatively useful in this case, is the printing the binary tree, because now we have to call our recursive function twice, where it's not exactly mutual recursion, but you can somewhat look at it as mutual recursion since there are two function calls, and this is really useful code if we are trying to implement something like exceptions, where it can get tricky once we are returning from that function. Anyway, the first approach that comes to mind in C when it comes to exceptions is setting the long jump and setting the long jump and jumping via long jump function to where you set your long jump initially. And that function, quite frankly, deals with stack unwinding very well, where it will unwind your stack to the point where you first initially set it via set long jump. But one thing that doesn't do particularly well and doesn't do at all, and even if you use long jump in C++, you're still breaking the object cycle, life cycle, and lifetime because of C++ RAII. And that's where it becomes extremely painful to use long jump, because even though it is performant, you can say, even though it's a system call behind the scenes, and it's sort of a, you can say, well, it's not exactly a compiler extension, but it's just the way that behind the scenes it will just work in your assembly. And it's sort of like a DLL or like a kernel implementation, so it will work on any operating system. So for that reason, and that reason alone, my first approach that I would deal with throwing an exception in C is to create a struct and a union, where my union will represent the return value of my function. However, the first thing that we are seeing here is that we don't have any return value in our type signature of quicksort, and that is a void. But if you do end up having a return value, you would just say here, I don't know, int and the name of your return value, or whatever your code logic is. So that is going to be the union that my function is going to communicate, or the call frame or my functions stack or call frame stack will communicate between each other in whether or not to return or continue with execution. And as we already well know, for example, if I'm throwing my exceptions somewhere in here in quicksort, let's say throw 1, and if I first call this quicksort, this is where the execution of my function ends. So not only is it halted, but we are returning, we should return, but the implementation of C++ exceptions is that of stack unwinding. So it would unwind your stack, and stop the execution right on the next line on. So now, to get back to the point, then I take that union and I wrap it up in my struct, where it is my union value and is my error flag. And my error flag is going to determine, it is essentially an enumeration. However, I try to use some hack here to reduce the size of my enumeration, because with this kind of enumeration, I would expect my enum to be 1 byte, but not like 4 bytes. And you would essentially treat it as a cast. But we're gonna talk about in a moment how to even get rid of this flag, where we can use null to determine whether or not our exception has been thrown. And it pays off, of course, in the grand scheme of things. And here I'm just making my variant value. So, and I'm using cleanup attribute of the GNU extensions of the compiler, just to showcase that at the end of our function lifetime, whether or not, or actually when we are throwing our exception, we will be cleaning up whatever we have in our function. And this is just purely for demonstration purposes. You would never have something like this in your quicksort, whatever. So my implementation of exceptions is to, and as you can see here, is just purely a function call. But since we're returning from our function call, each time now we are throwing, or we're trying to simulate throwing an exception, we have to stop at that point of time and keep returning up to the point where we can finally stop the execution of all of the functions or call frames on our stack leading up to that point of time. So if I return an exception, if I get an exception from here, I am straight out just returning that first call. And once I return that first call, and if that call here originates from this function as well is going to pick up where it left off, and we are ultimately returning from call 2, and we keep returning the initial erroneous call until we hit the rocks, and that will work exceptionally well. So the upside of this implementation is that I read online that, and I've researched sort of, that exceptions when thrown in C++ are from 100 times up to 1000 times slower than a typical return. So it's definitely a win for us there. But here's where we don't outperform C++ exceptions at all, and that is the happy path of exceptions. So the function call will be very costly if we are throwing an exception. But if we are not, the modern compilers figure out a way to have your code zero overhead runtime cost without using or even daring to touch the call unwinding. And that's how the happy path in theory works, but or functions, because I don't know how exactly it works. But I will try to find that out. But it's still at the compiler level, so it will be sort of difficult to re-implement that via explicit code. But since this is only the part one of this series, I will keep on researching and try to find out how does that work. So the only annoying thing uh, about my implementation here is that struct variant value is 16, and that is because even though we are using 8 and 1 bytes within our struct, there is still padding, alignment padding, so we have to get rid of this. And even though we tried to say this is only 1 byte, and so this essentially is in theory 9 bytes, but once the compiler applies the padding, the alignment padding, we will not get 8 bytes at all. So that's why I recommend that your error message or your exception should be thrown, or should be rather initialized or allocated on heap. And the pros of that is I can now check whether or not my exception is thrown if I just compare my exception with a null. So if it's a null, that means nothing was thrown. If it's not a null, now my exception is thrown, and that will work just fine. And just to take a step back here, the reason why our implementation is potentially slower than the C++ implementation of exceptions is that we will always have runtime cost, because we are doing a conditional jump here where we need to determine whether or not the exception was previously thrown. So even though we can throw nothing out of our function, still we have runtime cost, because we need to check each time whether or not something was thrown. So that is definitely where the C++ implementation of exceptions or modern compiler implementation really outshines this implementation altogether. So yeah, and because now let's get back to the initial point of improving our variant value. Now I can rewrite my logic, and I can sort of make or allocate my exception on heap, because what if I'm throwing my exception once? That's fine. I will not reallocate it ever again. But there will be some scenarios where we'll have to make a bunch of exceptions that would contain all sorts of metadata, not such as stack trace and stuff like that. I know stack trace is not natively, or it's not supported by the standard itself in C, but you can use some Linux libraries such as errorinfo. If I'm not mistaken, errorinfo, you can check that out on the Linux man page. Let me just look that up. See, I believe it was backtrace call or function definition. So it is defined in the execute info header. Yeah. So yeah, it's essentially this one here. So that's pretty much it. All right. So now also let's emphasize the fact of the matter that each time we're returning from a function call, we will be cleaning up our all of the variables that were defined at that point in time. And the problem with the long jump, as I've outlined earlier in this video, is that once we jump to the initial set long jump, the stack unwinding will work just fine, but we will not free our variables up to that point. But here, if we return from this current function or current call frame, we will be cleaning up our string implicitly in this case, because we're using the compiler extension. And once we return from that point on, we'll get some here, either here or there, and we will clean up the, in this case, string on heap or data on heap at that call frame, and so on and so forth until we return to the initial origin. So without further ado, let me just make this optimization, and we have to make that optimization because stack on, well, I guess stack, call stack will be pushed, or calls will be pushed onto our stack, and where the return of our function call will be taken into account, and we will be penalized performance wise once we return, because that return value will be taken into account in terms of building that call stack. And make sure to check out the series recursion into GoToLabels on this channel, including part 1, part 2, part 3, as well as turning quicksort into GoToLabels, where I break down all the structure of a call frame, where we have the function parameters, the body variables, and the return values. And that's where we get penalized at runtime. So always make sure to make your, or to have your struct as small as possible. And by the way, always make sure to write your struct members from the largest to smallest. That's how you give the compiler a shot at padding your struct in the best possible way, or in the most efficient way when it comes to your struct being as small as possible altogether. So you can say it will optimize your struct definition. Alright, so let's remove. First, I just remove the error flag and see what breaks. And we will have a lot of stuff, I guess, break at runtime, since this is a null conditional check, whether or not we have allocated and initialized our exception on heap. But in this case, actually it won't be on heap, by the way, because all of the strings are placed in the data segment of the program, so that's perfectly fine. All of these pointers or const character pointers will point to the same thing if they are the same. So as you already know, probably something like this in C and C++ evaluates to true because they are the same thing. They're the same pointers. Why is this not has no field error? Okay, hasn't loaded it up. Okay, I will also return, and I also make sure, as you've seen, to inline my function, because it will be quite expensive to make a call in our already expensive recursive call. So we have to make sure to cross all of our I's and dot or all of our T's. So that will be there, and also I'm checking for that here, and if I'm saying here my exception message not equal to null, that means, or actually equals to null, that means that my exception was indeed thrown. And that works just fine. And if we verify that there are no memory leaks whatsoever using Valgrind, you can see there are none whatsoever. And that is because we are making sure to return from that function all the way to the initial call frame that we pushed onto our call stack. And we are building sort of a structure where we'll get there. Throws one. Oh, 1 second. I might be exception. Where's my exception thrown? That's interesting. We should be seeing error raised at line 102, but I'm not seeing that. Value dot. Oh, if it's not equal to null, my apologies. So that is fine. That is now all good. Alright, that would be all for this video. So we broke down all the upsides and downsides of this implementation. Overall, C++ performs better when there is no exception thrown, way better. But when there is exception thrown, this one performs much better. And also, I didn't define this as a struct but a union. I always prefer a union, even in a case if we're not returning anything, just to keep everything as consistent as possible. And also our struct variant value is 8, since we made that optimization of getting rid of or making the error flag obsolete. So I always prefer to keep a union just to have everything consistent in case I'm returning something out of the function. And union, as you already know, functions in a way, well, let me just think about that now. We will need to have error flag if our function returns something. Here's why. A union by itself doesn't let us know which, or doesn't make us aware which union member is active at that point of time. So you will need to use the error flag in order to determine whether you set your exception or not. So in an implementation of returning from a void function, you would get rid of the error flag, and I'll make sure to document that here. So error flag while this is a great optimization for a void returning function, we will have to include the error flag in order to determine the active member of the union. In other words, whether or not we have thrown from a function. And you would use this struct, or actually you would use the variant where your, let's say your exception will look something like this. Exception, and that's where you would include your stack trace, exception message, and everything. Alright, I think that is all for this video. Let me just check if there's anything I missed. No, that's oh yeah, this will be now. I should have just used a line macro just to cut myself some slack. But yeah, I just wanted to make this video as soon as I've come up with this approach. Anyway, that'd be all. Thank you for watching, and let me know if you're interested in continuing this series. Take care. Till next time. Bye.